In this video, we start talking about the properties of determinant, and it is such an important topic in the course linear algebra, and you have to know all these properties extremely well. Let's start with the first one. And in this video, all the matrices we talk about are square matrix because the determinant formula only applies to a square matrix. Anyway, for the first property, we talk about the square zero matrix, which means all the entries are basically zero. Can you see why the determinant must be zero in this case? Because you see the fact is that if you use the cofactor expansion, for example, if you expand along the first row, what you are doing is writing the formula for the determinant to something like this, you see. So obviously there's a sign change term based on the checkerboard of the first row, and this term represents the sign change term. And after writing it down, you have to write down the product of the two things. The first thing is the matrix entry. The second thing is the minor to each position, right? But you don't have to find the minor because this one is zero, which means the determinant must be zero anyway. So I think this case is obvious. How about the determinant for other special matrices? For example, we can talk about the identity matrix. I claim that the determinant must be 1. Can you see why? For example, if you look at the 2 by 2 cases, it's actually so obvious because what you are doing is you are applying the determinant formula AD minus BC, and obviously the determinant is 1, and starting from the next one, I hope you see what's happening. You see? Look at the 3 by 3 matrix. Of course, now you can expand it along the first row by the cofactor expansion. So in that case, you're having something like this, but you see, the second spot and the third spot are both zeros. So it means when you do the cofactor expansion, only the first term is non-zero. The first term is what? The first term is basically plus 1, which is the matrix entry itself, times the minor at this position, which is the determinant. You see, by deleting the first row and the first column, so you are looking at determinant of this. And this one itself is the determinant of a smaller size, right? And of course, it means the determinant must be 1. So it means at the end, the determinant is going to be plus 1 times 1, which is of course 1. And as you can see what's happening, if you look at the 4 by 4 identity, I claim that the determinant must be 1. I hope you can see why, because you can do the ex expansion for the cofactors on the first row, and you could notice that when you write all the terms down, only the first term is non-zero, which means the first term is going to be 1 times the determinant of the minor of the first position. But you are getting a smaller determinant where now you're taking the determinant for the identity of 3 by 3, right? And we understand this one has determinant 1 already. So that's why the determinant of identity must be 1 for all sides, basically. And let's look at the property 3. We talk about two special kind of matrices, which are the upper triangular matrices and the lower triangular matrices. And they are easy to understand. Upper triangular matrices essentially means the non-zero entries can only occur at the diagonal or the entries above the diagonals, like around here. But off the diagonal and below the diagonals, they are all zeros. And for the lower triangular matrix, it takes the same meaning, but in the opposite sense. So for example, you can look at these two 3 by 3 matrices M and N. You can see the first one is upper triangular because of the fact that the terms below the diagonal are all zeros. And similarly, for the N, it's going to be lower triangular matrices because only the terms which are on the diagonal and below are non-zeros, right? So these are the upper and lower triangular matrices respectively. And what is a special thing about that? Let's look at the determinant now. So just to illustrate the idea, as example, let's look at the matrix N. If you look at the determinant of N, what you can do is you can do the cofactor expansion on the first row because you see, because these two terms are zeros. There's a benefit if we expand it on the first row because there's only one term which is non-zero, which is basically the first term. The sign is positive on the top left corner. So you have to multiply the matrix entry with the determinant of the 2 by 2 matrix after deleting the first row and the first column, right? So we are looking at this matrix. Basically, it is 8, 0, 11, 9. So I hope you see what's happening. And of course, this matrix, you see, because this spot is 0, basically it means that the determinant of this 2 by 2 case is just 8 times 9, right? These are the two numbers on the diagonal. As you can notice, this answer means what? This answer means instead of applying the cofactor expansion on row 1, what you can do is you can simply multiply the numbers on the diagonal. Give you a sense that for this particular matrix N, the fact is that to find determinant is very straightforward. We don't even have to apply the official formula, which is the cofactor expansion at any row or column. We can simply multiply all the numbers on the diagonal entries. And I can tell you that this is actually in general true for all kind of matrices as long as they are upper triangular or lower triangular. For example, for determinant M, what we do is we can simply just multiply all the numbers together on the diagonal. So it means the determinant of M is 6. So let me write down the statement here in black color. So please look at my statement here. The determinant of these matrices, which are either upper triangular and lower triangular, it must be equal to the product of just the diagonal entries. And you can take a look at the identity matrix, which is a special case of an upper triangular matrix or a lower triangular matrix. And there's a big reason why the determinant of an identity matrix must be 1. And let's look at the next property now. So now I'm claiming that if the matrix actually has a 0 row or a 0 column, the determinant must be 0. Can you see why? You see, I think the answer is obvious because, for example, if you look at the determinant M, let's say one of the row is totally zeros. All entries are zeros on this particular row. We can just do cofactor expansion on this row, right? So you see, when you write down the cofactor formula here, the fact is that every term you must have zeros because 0 is the matrix entry. You have to multiply it to the minor at that particular position, right? And you have to do the alternating sum of all these terms, and that's the reason why this summation must be 0. And similarly, for the n, you can actually take the cofactor expansion on this column to get determinant 0. So I think the property 4 is quite obvious. And let's look at a more interesting property 5 here. So let's say now if you try to swap two rows of the original matrix M and to get a new matrix M prime. So for example, I'm talking about a situation like this. For example, if you have a 2 by 2 matrix M like this, what you do is you can swap the row 1 and row 2. So it means the new matrix is actually having the row 3, 4, which is the same as the row 2 in M, as the row 1 for the new matrix now. And similarly, the second row of the new matrix is gonna be the same as the row 1 of the original matrix. We can call this new matrix M prime. And please notice the relation of determinant among the two matrices here. I claim that the determinant of the new matrix after swapping any two rows or two columns is gonna be the minus of the determinant of the original matrix. If you look at this particular case now, I think it's obvious because for M, determinant M is gonna be 1 times 4 minus 3 times 2, and determinant M prime, which is the new matrix, is gonna be 3 times 2 minus 1 times 4. You see, if you look at the determinant formula now, they are opposite to each other, just a difference of sign, right? And I claim that this property is also true for the matrix having a bigger square size. And then we can look at the property 6. For example, let's say M now has a special property that on two rows they are the same rows, or maybe there are two columns they are the same. For example, we can look at such a case. Like, for example, I can say M is something like that. So you see, in this case, row 1 is exactly the same as row 2, right? Or you can look at the other matrix N. Let's say you have something like this. The column 1 is same as column 2 in this case, right? And in this case, I claim that the determinant must be 0. Can you see why? You can try to look at the property above, which is the property 5. Let's say now the M has two identical rows. What you can do is you can swap these two identical rows to get a new matrix M prime. So please think about it. For example, if you have the M now, what you are doing is you are swapping the row 1 and row 2, and you are not changing the matrix at all, right? Because I'm forcing you to swap the two rows, they are originally identical. So please notice that it's obvious that M prime, of course, is the same as M. You are not changing the matrix at all. But if you look at the property above in property 5, we understand that if you swap any rows, you see if you swap any rows, theoretically speaking, by 5, property 5, and we know that the determinant of the new matrix must be the minus of the determinant of the original matrix, right? However, We understood it already that in this particular case, because the two matrix M and M prime are the same, like this particular example, which means, of course, because they are the same matrix, the determinant of them must be the same, right? And now please try to look at these two facts together. Let's say the fact star and the fact double star. If you combine them, you could easily see that the determinant of M must be 0, right? Because now you see when you combine them, you're having a equation like this, and you see determinant M actually equals minus determinant M, which means because determinant is a real value, so you can push this term back here, so it means 2 times determinant M is actually 0. It gives you a sense that determinant M itself must be 0. So it's quite an interesting fact. It means instead of using the fairly complicated determinant formula by the cofactor expansion, what you can do is you can take a look at the matrix M first. If there are two rows, they are identical. We understand it already. The determinant must be 0 without applying the determinant formula. So in property 7, I would like you to do a row operation on the matrix M to get the new matrix. Let's say what you want to do is now you want to multiply K, for example, on certain row. Let's say it's the row I. And I think this fact also applies to any column anyway. So you can do either a row operation or column operation. You have to multiply just one row by a constant K. You can choose any row you want in the original matrix, just multiply it by K. And I claim that the determinant of the new matrix now is going to be K times the determinant M. So in case if you don't fully understand what I'm talking about in this process, for example, I'm saying that, for example, if you have a matrix like this, what you can do is you can multiply, let's say, the row 1 by 5 times row 1. It means after this process, you are leaving the row 2 unchanged, but the first row is multiplied by 5. You're getting this. I claim that the relation between these two determinants is like this. Can you see why? Because the fact is that if you do the cofactor expansion on the particular row which is changed, on this row operation, what you look at is the following. See, that's the summation formula for the determinant for the cofactor expansion on the row I. And you see the fact is that this element for the matrix M prime, which is like the row like this, which is changed, it is basically the same as K times the original matrix entry at the same position, right? So it means each term now has the constant K. So it means I can pull out from the summation formula. So it means you're left with the formula like this for the determinant of our new matrix. But however, this summation of the alternating sum of all these terms is basically the determinant of the original matrix M, right? Because that's the formula for factor expansion on the row I, right? And it gives you a sense that theoretically we can actually prove it. And it's not difficult to see anyway. So in property 8, we'd like to look at the scalar multiplication. For example, if I ask you to multiply a scalar matrix. So let's look at a simple case like this. What you are doing is if you multiply 5 to the whole matrix M, this 5 is distributed to all numbers, right? So it means this new matrix is going to be this one, right? And I claim that there's a good relation between this, but it depends on the size of M. Say now M has size n times n. I claim that the determinant of the new matrix after the scalar multiplication is going to be the original matrix M is determinant is multiplied to k to the power n, and n is the number of rows or the number of columns you have in the original matrix M. Can you see why it must be true? Because you see, you can break it down into a couple of row operations. For example, you can look at the row 1 first. You're changing row 1 to k times row 1. Since this matrix is actually the same as the original matrix like this, for the M, let's say M is listed by the row, and now this first process, we're just changing the first row, right? And all the other rows are unchanged, basically. And you see the second one, what you can do is you can actually change the row 2 by multiplying by K, and it means after this, what you have is the row 1 is changed already, and now you're changing the row 2, but row 3 remains unchanged, right? And after, let's say, n steps, each time you see you are multiplying k to the particular row I, You have to do it n times because I'm assuming that there are actually n rows. At the end, you are going to get the final step. This matrix is going to be the scalar multiplication for the whole matrix, right? And if you recall the previous properties, which is property 7, the fact is that, for example, this matrix in the second step, it actually has the determinant k times determinant m, because you are doing the row operation multiplying k to only one row. And this fact we learned in property 7. And for example, this matrix is gonna be having the determinant k times the determinant of the last matrix is k times determinant of the last m, right? So it's going to be k squared times determinant m. And obviously, because you are doing it all together n steps, due to the fact that m has n rows, we understand the last one must have determinant k to the power n times the determinant of the original matrix m, right? So let's look at the matrix now in property 9. This matrix has a special property that one of the rows or one of the column is actually the multiple of another row. So I'm saying something like that. For example, the m, if you list it by the rows, what I'm saying is that, for example, let's say you have a row I, and there's another row. It actually looks like it is the same as row I, but each entry is multiplied by a certain constant k. And for example, I can give you this case. So you can look at this one. If you look at this matrix, it has a special property that I hope you notice. The fact is row 2 is the same as 4 times row 1, right? And that's what I mean by one row is the multiple of another row. And in such a case, I claim that the determinant of this matrix M must be 0. Can you see why? Because you can imagine that you have actually applied a scalar multiplication for only one row as a row operation from the original matrix. Let's say now this original matrix is what? This original matrix has the property that the row I, you see, is identical in two positions. If you do the row operation like this, then you are getting something like this, right? So you see, we learned in property 6 that this one must have determinant 0 because of the fact that it has two identical rows. We have seen this property already. And now if you multiply like k as a constant to another row, by another property we have learned, which is property 7, we understand that now this determinant of this M is going to be k times the determinant of the old matrix M naught. And because this one is 0, we understand now the determinant M is actually 0, right? So now in property 10, we'll look at the property where, let's say now you have a matrix M, the first row, you actually have two terms added up together. I claim that the determinant of this matrix M is actually the sum of the determinant of two different matrices. And the first matrix actually takes the first row by using only the first term from the original matrix M on the first row. And the second matrix has the fact that the row 1 actually has the second term from each term from the original matrix M. And I would like to emphasize that the remaining terms here, they are all unchanged. So that's my claim here. The determinant of original M can be split like this as the sum of determinants of two different matrices. And I hope you can see why. Because, for example, if you look at the cofactor expansion on the row 1 for the original matrix M, you can write it like this. And you see this formula can be split into two summation, right? You see after the split, this one is basically the determinant of the matrix, the first one I'm talking about. And this one is basically the determinant of the second matrix I taught when you both use the first row as the cofactor expansion. And that's a simple reasoning here for property 10. And let's look at the last property. So please look at the current operation we are doing on the particular row for a matrix M. On the property 11, you see this kind of row operation is very common and we have seen it so many times. Such operation is used when we solve a linear system in Gaussian elimination, or we are trying to use the row operation method to get the inverse of a matrix, right? We use it just all the time here. And you see the fact is that surprisingly, I claim that after such kind of row operation, the determinant of the two matrices are the same. And can you see why? Because based on the previous property 10, we understand that the determinant of M prime is going to be the sum of the determinant of two different matrices. For example, the first is I can look at it like this, right? You see, that's the first matrix with only the first term, and the second matrix actually has the second term, right? So in case you forget something about property 10, you can take a look at that again. And now I claim that the second matrix actually has determinant 0. But before explaining that, let's look at the first matrix. This determinant is basically the determinants of the original matrix M, right? They are the same. They are the same. So which means if you are able to show why the second matrix has determinant 0, I think we are able to arrive at this fact already. So this determinant must have determinant 0 because you see this row should be the position for row I. But this row J means it means somewhere above this row or below there must be certain row which is row J, right? It means what? It means you have a row J originally and there's another row which is row I, but you change this row by this term, which is the term minus k times row J. So now you have a matrix like this. And we have explained it already in a previous property. So I think it's basically property 9. You see, property 9 basically explains that if you have a situation like you have one row, which is the multiple of another row, the determinant must be 0. So I'm using a property 9 here, which means if you combine the two previous property 9 and 10, we're able to arrive at the fact that this second determinant must be 0. It means the determinant of the m prime must be the same as the determinant of the old one, which is this. You see they are the same. So it's quite a surprising fact, and that's the end of this video.